Hello, hello. Yeah, on you. Hello, hello, hello. Hi guys, you are welcome to God Academy. In this lesson, I'll be taking you through introduction to multivariate calculus, and I've listed a couple of stuff you're going to touch in this video. So we'll be doing 3D coordinate system, a touch on equations of lines and equations of planes, domain of multivariable functions. Then we have quadratic surfaces, cylindrical coordinates, polar coordinate, then spherical coordinates, and that'll be all for this tutorial. I'm going to wrap up since equations of lines and equations of planes are all revision from algebra. I wouldn't spend so going to rush through. And please, if this is the first time you have been on the channel, right, and make sure you share to your friends so they will also benefit. Please, if this is the first time, make sure you share to your friends. Okay, let's get started. This is calculus with several variables. And I believe if you are new to this course, you'll be having several expectations about what at all is calculus with several variables. Primarily, we are used to the coordinate system where we have simple y and we have x on our axis, right? And we are entering into multivariable. Multivariable means two or three or anything more than two, right? With regards to the first calculus you did, or calculus one, it's always f of x is equal to something. Always a function of y, a function of z. But in this chapter, we are going to look at functions of x, y, z, or a function which is in terms of x and y, f of x, y, z. So that is what you're going to handle. Now let's talk about the 3D coordinate system. 3D coordinate system. When you say 3D coordinate system, you believe 3D. I believe 3D. You understand what 3D is, right? So in the row number notation, when I write R with a double arm like this, or let's say like it's what row numbers, right? When I write this same thing but squared, it means that it is in the 2D space, okay? When I write this same thing and I make it cube, it is in the 3D space. So take note of this representations. Now, for me to explain this nicely, let me give some sort of problem here, okay? So it says that graph S is equal to 3 in R squared, then R cube, right? So we are supposed to graph X is equal to 3 in terms of R, in terms of R squared, in terms of um R cube, right? So in terms of real number system, right? In terms of real number system, remember that if I want to locate X is equal to 3, what do I do? On my R, you are only entitled to the simple number line because you are in only one dimension, that is in a set of raw numbers. So I'll locate, let's say here is 1, here is 2, here is 3, right? So my 3 is simply S equal 3 is simply locating the point 3 on a raw number line, okay, or something like that. Now in our 2D domain, that is where we come to our normal Cartesian coordinates, where we have our y and we have what, our x. In our 2D domain, if I want to locate S is equal to 3, what do I do? On my y, let's say I have 1, 2, and I have 3. On my x, 1, I have 2, I have 3. If I want to locate S is equal to 3, remember how it is done. S is equal to 3 always forward on the y-axis. It should be parallel to this. S is equal to 3, there is it. And y is equal to 3 will be parallel. Okay, so I'm sure you are seeing how it is. Wait, oh no, I think I'm making okay, sorry. So this x equals 3, sorry, I was looking at line y is equal to, we have that one, and we have s is equal to, I'm coming. So when you locate 3, so let's see the changes. Okay, from the R domain, which was the 1D, it was just a point. In the 2D, you can clearly see that it has become what, a line in the two-dimensional. Now let's move to the 3D. In the 3D, I'll have my simple 3D coordinates. I have my y here, I have my x here, and I have my z here, right? So let's say 1, let's say 2, let's say 3. Let's say I have my x to be 1, my x to be 2, x to be what, 3, right? My y to be what, 1, 2, 3. This is a three-dimensional space, and I want to draw s is equal to 3. For here, look at how it's going to be. It's going to be a plane which cuts across our coordinates. S is equal to what, 3. So it's going to cut across here. See, it is passing through the 3, but it's going to be a plane. So you can you imagine, we move from dots we came to what, a line, from line we are in a plane. So that is the transition. Or when you talk about 3D, your shape tends to have a fixed let's say that three-dimensional view, because it will have x and it will have y what, representations. So this is a transition which I want to open your eyes to. Now quickly, let's do a recap of equations of a line. Equations of a line. This is a course treated in algebra, but since you are in the 3D space, let's revise and appreciate how the equations of lines was derived. In my 3D space, as I have my y, I have my x, and I have my z here, this is my center, right? A line in a 3D space is not the 2D we know. You know, basically, if you want to find the equations of equation of a line, what do? You draw your y and you draw your what, x, and your line is here. The only thing I need to define the direction of a line in 2D is my gradient. That's all. So once I have my gradient m, I'm fully sure that my line is indeed in that direction, slope. Now let's talk about a line which is in the 3D space, a line crossing this way. How do you define the direction of this line? Gradient is not enough. How do you define a line which is clearly moving in the 3D space. So this is where the concept of vectors gets grounds, right? So now, for me to define the direction of a particular line, I need a vector, which is a known vector, and that known vector, I surely know the direction. So I'll use the direction of that known vector, and since that known vector is going to be parallel to my line, it becomes my direction. I say it again. For us to define the direction of any unknown line, which we want to know the equation of that line, you first have to identify a known vector in that same space and use the direction like a known parallel vector. Okay, so let's say I have another vector emerging from this side. It's emerging from this side, and I know it to be vector v. Okay, so since vector v and our lines are in parallel, then I can fully describe the direction of my line using vector b. That's all. Okay, yes. Now on this line that I want to find the equation of a line, always you need one point, at least one point on a line before you can find the equation. Let's say that point is p naught, which I know. Okay, so the vector from my origin to p naught becomes r naught. Okay, that's the vector r naught. Then I will locate an unknown. You know, the goal of finding equations of a line is to randomly find any point on that line. So if I'm able to find any arbitrary point aside a known point, then it means I have the equation of that line. So I can find any point on at any instant. So assuming I'm to find a point P on this same line, then that one I'll have its vector to be what? R. Okay, like this. Now we have P naught and P, these 2 points. The vector connecting P naught and P, remember it is exactly parallel to what? My vector, which is here, which is my known vector. But I can randomly say that it is represented as, let's say, A. Okay, let's say this vector is represented as A. Now remember the triangle of vectors, and for us to sum vectors, this is moving this way, this is moving this way, and this is moving this way. So the triangle law is saying that if you want to find, if you have, three vectors using the same order, this vector which is closing these two vectors is equal to the sum of the two vectors. So r naught plus what? My a. So check it again. So I have this vector r, which is moving here, and it is close. You see, this is going here, this is going here. Then r is closing the two. So by addition of vectors, we are going to have r to be equal to the sum of r naught and the sum of what? A. It's, let's say it this way. Let's say there is a shop here. That shop is selling coffee. You are standing here. You want to go to the coffee shop. Either you take the straight route or you what? You first move to this point. After reaching here, you continue this way. So that is the idea of the sum of what vectors. Okay, so if I have r vector r which is crossing this way, then I can say that my vector r is simply equal to r naught to what? To a. That is all. At this point, remember that a here is parallel to our known vector, and every parallel vector is equal to a scalar multiplier of the known vector. So my vector a, when you say two vectors are parallel, it means that it is a scalar multiple of the other. It may be collinear. Once it's collinear, it means that a scalar is 1, right? But if it's not collinear, it will simply be parallel in space. So with that in mind, I can replace, so instead of k, let's say t, popularly used, so t like this. So I can replace my a with what? R is equal to r naught plus what? PV, like this. Where t is any arbitrary constant, okay? So this is what we call the vector equations of a line. Okay, this is a vector equation of a line. Now, my r naught here, assuming that my point p naught is given as x naught, y naught, z naught, and my point p, arbitrary point, is x, y, and z, then my r naught from the origin, that is op naught, is simply going to give me what? X naught, the same x naught, y naught, and z naught, plus, now let's represent our known vector in space as a, b, c, right? That is the content of the vector. So these are all vectors. Oh, no, sorry, this is a vector, so you angle bracket. This is just a coordinate. So with the known vector, we call the numbers ABC as direction numbers. Okay, we call it direction numbers because it gives the direction of our line in space. So here we are just trying to derive or break our vector equation down. So let me just circle this. So this is a vector equation nicely. So once I have this down, then I can go ahead to simplify here. So my R here, which is also for this, is OP. OP will give me vector X, Y, and Z is equal to my R naught, which is vector X naught, Y naught, then Z, plus my known arbitrary constant T, and my vector V, which is A, B, and C, right? We can make it in the column form like this. Is equal to X naught, Y naught, Z naught, nicely, plus T multiplying A, B, C, right? At this point, you are going to find what we call the parametric equations of a line. So looking at the very first one, my X is equal to X naught plus what? 80, right? My Y is going to give me Y naught plus BT. Then my Z is going to give me Z naught plus what? CT. These are what we call the parametric equations of a line. Now, after deriving a parametric equation, we want to do away with the arbitrary constant T. We don't need constant before we can determine our um, equations of a line. So we do away with it. So make T the subject in all equations. From the first equation, T will be equal to X minus X naught over A. T will be equal to Y minus Y naught over B. T will be equal to Z minus Z naught over C. Once I have this listed, then it means I can equate all of them. Is that not it? Because they are all T. They are the same. So therefore, X minus X naught over A should be equal to Y minus Y naught over B should be equal to Z minus Z naught over C. This is what we call the symmetric equation of a line. So these are the three equations of a line that characterize it. You have the vector equation, you have the parametric and the symmetric equation. One may ask, what about if A or any of the direction numbers is zero? You end up getting over zero, but please we don't, assuming A is zero, we don't just bring it. You make it X minus X naught, okay? We don't bring it. You can't say it's undefined, no, we don't do that here. So we just say that it will be in the same direction as what that particular hot line. That is the idea, but we don't say it is undefined. No. Now, once we have that done, I think we have clearly proved all the equations of a line. So just as a recap, let's um let's try and see this here. Okay, write down the equation of the line, sorry, that passes through the point. I have point P to be equal to 2, negative 1, 3, and point Q given as 1, 4, negative 3. Says write down all the three forms of the equation of line. Write down the three forms of equation line. So there's a question on board. So we are supposed to solve this problem here. Solve our problem, we need our 2 points on the line, and I think that is enough for us to get the direction of this vector, right? So that's going to be vector PQ. So this is also another way. So what's vector PQ? Vector PQ is equal to OQ minus OP, right? Therefore, I'm going to have my OQ 1, 4, negative 3 minus my OP negative 1, 3, right? And nicely, what am I going to get? 1 minus 2 is negative 1. 4 minus minus 1 is 5. Negative 3 minus 3 minus. Therefore, my direction vector PQ, which is also equal to my V, given as negative 1, 5, close with angle bracket because it's now a vector. Once you get your direction vector, you only take one of the points and you find your equation. Using vector p and point p and vector, let's quickly write our vector equation. Our vector equation, which is r is equal to let me use my yellow tool, which is vector r is equal to our vector r naught plus what tv vector this, right? So now our r becomes what the unknown, right? So x, y, then z nicely should be equal to our r naught is giving us the known and I say we are using the point p 2 negative 1 3 plus t. Then our direction vector now is what negative 1 5 and we are done. This is simply your vector equation. Simple as that. Once you have your vector equation derived, obviously you know you can straight away find your parametric equation. This gives x, y, z equal to 2 neg 1 3 plus t multiplying negative 1 5 negative. So at this point, s is equal to 2 minus what t, right? I'll have y to be equal to negative 1 plus 5t. I'll have z to be equal to what? 3 plus minus 60. These are what we call the parametric equations of our line. We are done. Now we move to the last one. The last one, what do? We are just making t the subject, is that not it? So what do? We have t to be equal to 2 minus x and y. For this y side, 2 be equal to what? And we cancel 2 be equal to, I'll have y plus 1 over 5 is equal to t. Then here I'm going to have c minus 3. No, let me do it the other way around. So I'll have 3 minus z over what? X to be equal to t. Therefore, we say 2 minus x is equal to y plus 1 over 5 equal to 3 minus z over 6. And this is what we call the parametric equation of the line. And that is all about equations of a line recap. Quickly, let's do the equations of a plane. Equations of a equations of a plane. How do we derive the equation of a plane? What actually do we need to get the equation of a plane? So let's see. If I have a plane is just a 2D surface, right? So I'll first draw my Cartesian plane line. Yeah, have my y here, my x, and my z up on top here like this. So assuming that I do have a plane on top like this, so this is a typical plane, right? So this plane is in parallel with the xy plane. So this plane here, I want to define its equation, or I want to derive a relationship so that I can find any point in a plane. But a plane is said that to find the direction of a plane is so hard. How do we determine the direction of this plane? Fully determine it. So this is where the concept of cross products, if you remember from your algebra, comes in. The same thing for every plane. I'm going to find, we have a known point P naught, right? Then I have an arbitrary point P, which I want to find the values of that point. Remember, P naught is always equal to what? Our x naught, y naught, then our z naught. My P, which is arbitrary point, is my x, y, then z. Nicely. Once I have this to the origin, I'll have my r naught, and I'll have my what? My r. Then you can clearly see that the vector p naught will then become what? Will becomes my r minus r naught. That not it, because this is my vector here, my vector here. So here we are trying to find the vector p naught, but we can still maintain p naught. But what's the essence? How do we define the direction? What do we need actually? Here we are not going to find a vector. A vector in space is not enough to determine the direction of a plane. If a plane is moving this way and a vector is moving this way, you can't say it is the directional. Because of that, we use what we call the normal. So a normal is any vector which is emerging from the plane, so that this vector is 90 degrees to any known point within the plane. So if I take the normal of a plane, any point I select randomly, right? If I create a vector between any 2 points within the plane, it is going to be perpendicular to my normal. That is why we believe that the normal is the only assured parameter which fully describes the direction of a plane. So therefore, I'll make my normal emerge from this plane like this, and that's going to be 90, right? So then remember from your dot product that any two vectors which are orthogonal, their dot product is 0. Is that not it? So therefore, my normal, which is n dots, let me use, so my normal n dots, my vector, which is r minus r naught, should be equal to 0 using the dot product, scalar dot product. Therefore, my n r minus n r naught should be equal to 0, right? Yep. So here you can say that n r should be equal to n r naught. And that is the vector equation of a plane. This is simply the vector equation of a plane. Now, let's derive the rectangular equation. Remember that I said r is going to be what? Our x, y, z, r naught is going to be x naught, y naught, z. Okay, so at this point, even here, my n is a normal vector which can be represented as any random a, b, c, which is similar to the direction numbers we had in the equations of a line. So a, b, and c are what you call direction numbers. So for that reason, I'll have my a, comma b, comma c dots. Now my r minus r naught, I have my r, which is a vector within. So let me clean this here. So dots. This, my r is what? X, Y, Z dots. Sorry, minus my r naught, x naught, y naught, comma z naught. Is that not it? That close should be equal to 0. So this is still the same vector equation of a plane. You have this a, comma b, comma c. Then within this, I'm going to have x minus x naught, y minus y naught, comma z minus z naught. And these are the direction numbers of, sorry, these are just, okay, we are still on point. So at this point, our vector equation has been simplified. Remember, dot product says that you take one dimension here, one item, you multiply it by the corresponding item, then you add. So I'm simply going to have a multiplying x minus x naught plus b multiplying y minus y naught plus c multiplying z minus z naught should be equal to 0. At this point, you simplify, you are supposed to get your rectangular equation of a plane. As simple as that, right? So with that known, let's just try a simple example and move on. So determine the equation of the plane that contains the point P given us 1, negative 2, 0, Q given us 3, 1, 4, R given us 0, negative 1, 2. Nicely like this, right? Determine the equation of the plane that contains the points P, Q, and R. How do we solve this? So for you to define the equation of a plane, you need 3 points. 2 points is not enough, right? So here we need what you call the direction, and the direction of a plane is the normal n. So I have the normal vector. How do I find normal vector? So to find a normal vector, you use what you call the cross product. So I need vector PQ and vector PR. Then I'll find a cross product to get the normal vector. Okay. So let's find vector PQ. So PQ is simply equal to OQ minus OP, and I'm going to have my OQ, which is 314, minus my OP, which is 1 negative 0. So this is supposed to give 3 minus 1, 1 minus minus 2, 4 minus 0, which is, so therefore PQ given as angle 2, 3, 4. And you're not done. PR given as OR, OP, right? My OR 0, negative 1, negative, gives me 0 minus 1, negative 1 plus 2. Therefore, I'll have my are given like 1, 1. Now we have PQ, we have PR. So find a cross product. So cross product PQ cross PR. Just revise. This is a simple revision. So I'll have my 3 by 3 IJK, then my PQ will follow, my 3, then 4, then my PR negative 1, 1. I'll find the determinant. I'll have plus minus plus. So I will start, open bracket, cancel everything. I'll have 3 times 6 minus 1 times 4. So 6 minus 4. And that is what I'll have minus j. Open bracket, it will cancel everything. I'll have 2 times 2, 4. Minus 1 times 4 is what? Plus 4. Plus k. Open brackets to nullify everything. 2 times 1, is that not it? So 2. Minus what? 3. So plus 3. Therefore, here I have 2i minus 8j, then plus 5k. So this is now our direction number. So our n will then simply be equal to, just take the coefficient 2 comma negative 8 comma what 5. As simple as that. Once you have our n, we take any of the point. Let's take p, as simple as that. So I'm going to have my n 2 negative 8 5 like this, right? Dots my x minus x naught. So x, my x naught is what? My p, right? So p1, right? Comma my y minus y naught, but my y naught is y plus 2, comma z. Z naught is 0, equal to 0. Therefore, I simply have 2 times x minus 1 minus 8 times y plus 2 plus 5 multiplying z for 0. 2x minus 8y minus plus 5z is equal to 0. X minus y plus 5z equal to 18. And for simple. So now let's close chapters on our revision and quickly move to the next thing on board. And we are going to talk about finding um domain of a multivariable function. But before then, let's talk briefly about quadric surfaces. Quadric surfaces. But before you talk about the domain, you should appreciate the quadric surfaces. Now, so I have quadric surface. So for quadric surfaces, what do I mean? If I give you an equation, you should be able to tell which surface it is. Okay, that one I'll leave it for you to go and find all the quadric surfaces. Try to memorize how it is. S squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. This is what we call ellipsoid. So an ellipsoid draw is going to be hard, but let me try. I'm going to have this. Let's say this is our y, this is our x. It's like a sphere which has been compressed into this way. So this is just a sphere, like something round, right? Something round, but it has been compressed this way. That's an ellipsoid. Then I have an equation: s squared over a squared plus y squared over b squared plus z squared over c squared. Sorry. So c squared. This is equal to, so see the difference. If you have s squared over a squared plus y squared over b squared is equal to z squared over c squared, we have what we call a cone. So in 3D, if you get any equation like this, you define it as a cone. As a cone. I don't want to go into the detail of it. So simply, if you have this, I have my y, I have my x, I have my z, right? And a cone, obviously, yeah, like this is a cone. Let me add one important one: cylinder. S squared over a squared plus y squared over b squared is equal to 1. That's the equation of a cylinder. Equation of a cylinder. Okay. So here, Remember how a cylinder looks like. But let me do it. Let me draw my cylinder. Have your cylinder. Try. So my x coordinate will move out and y will move out here, popping out. That's the equation of a cylinder. Take note of this. You'll be dealing with cylindrical coordinates. Then you can have a sphere, equation of a sphere, x squared plus y squared plus odds. C squared is equal to a 1. That's going to be equation of a sphere with radius 1. So all these numbers 1 is just with radius 1, okay? They are just primary, can have different. So this is the equation of a sphere, and you know how a sphere is. So we'll be talking about spherical coordinates as well. So let's quickly jump into finding the domain of a multivariable function. How do you find the domain of a multivariable function? Domain of variable. As I said earlier, a multivariable function, we have f of x, y, f of x, y, z. You can have 4, 5, 6, 7, 8, and more variables. But to our level, we are only interested in 2 and 3 coordinates. Okay. So now, the domain of a multivariable function. Let me use some questions to explain. Remember that when you're doing domain of a function, calculus 1, you were getting a simple, let's say, real number. So most we say that a set of real numbers so that x is this and this, right? Now, for the domain of a multivariable function, you end up that the domain of that function is a cone. The domain of that function is a cylinder, it's a sphere. That is the difference. We don't normally get a linear or just a simple point as a domain. So let's take the first example. So actually find, it's a preamble. Find the domain of the following functions. Please pay attention here and so that you can go and practice more when you are learning. F of x comma y equal to the square root of x plus y. What is the domain of this function? X plus y all under the square root. First of all, remember domain. Mathematics simply a set of numbers upon which this function is defined. So what are the set of numbers that makes this function here defined? In the presence of a square root, you believe that x plus y should be greater than or equal to 0, which is a fact. This becomes our domain, right? How do we represent this domain? So if we do domain, graphically, remember this is the same as equation s is equal to what? Negative y, which is um, a particular line crossing the what? If it is s equals y, it will move this way. S equals negative y, so to move this way, right? So it is passing through the origin. Then it said that it should be greater than what? 0. So our region of interest falls this side. So this is our domain. Our domain is such that x, y, is such that x plus y is greater than or equal to 0. As simple as that. That's all. With your graphical, so it is a region beyond the equation or the line passing through the origin. As simple as that. Let's check nice ones. F of x comma y is equal to square root of x plus square root of y. With this, we're going to have x to be greater than or equal to 0, y to be greater than or equal to 0. Okay, so I mean it's the same thing as we did. They are different. Okay, they are different. You treat this separately from this. Now, how do you present this graphically? When I have an equation, all my x is greater than 0 for this part, right? Then all my y is greater than 0 for where? For at this side, like up this whole side. Therefore, our region of interest for this function then becomes this and this. So our first quadrant, that's all. First quadrant. So we have x comma y, that s is greater than or equal to 0, y is greater than or equal. Simple as that. Then our next problem, nice one. So I'll have natural log f of x and y is equal to natural log of 9 minus x squared minus 9y squared. Now here, what you just have to do is to remember that what makes the natural log function undefined or defined, meaning that 9 minus x squared minus 9y squared should be greater than what? 0. As simple as that. It should be greater than 0. It shouldn't be equal to 0. We don't entertain 0 in the argument of natural log. At this point, you push and you get x squared plus 9y squared is what? It's less than 9. Divide through by 9, we're going to have x squared over 9 plus y squared is less than 1. This is a perfect equation of an ellipse. Equation of an ellipse. Okay. So this is an equation of an ellipse. That's what I'm saying, that the regions are mostly something you have to refer from the quadratic surfaces. So it's an ellipse touching plus and minus 3. So let me draw it here. I'll have this negative 3. My ellipse will be touching these 2 points. Then it will be touching 1 on the y-axis. That's my region of my domain. If I were to state the domain, it's very simple. The domain is x comma y is such that x squared over 9 plus y squared is less than 1. That's all. This is the domain. It's not anything big. It's not difficult. Okay, let's this a beautiful one too here. A function f of x, y, z. Okay, is given as 1 over the square root of x squared plus y squared plus z squared minus 16. So these three variables, right? What's the domain of this function? The domain of this function will say that the denominator shouldn't be 0. Therefore, x squared plus y squared plus z squared minus 16 should be greater than 0, not greater than or equal to. Take note, should be greater than 0. Once you have that done, you have x squared plus y squared plus z squared greater than 4. This is equation of a sphere. Therefore, the domain of this function is a set of numbers outside a complete sphere of radius 4. Take note, a complete sphere of radius 4. This is 4 squared. I mean 16, okay, of radius 4. So it simply, you can see. So the region is greater than what? 16 or 4 squared. And this is simply a radius, a sphere of radius 4. And the region is outside this domain. Let's write a final interesting question. F of xy equal to x over natural log of y. Can you try this and see if you can get this right? X over ln y. X over ln y. X over ln y. How do you solve? How do you solve this? So to solve this, you definitely know that our ln y shouldn't be equal to 0. I mean, it's something you should know. If the whole expression here becomes 0, the entire thing becomes invalid. And remember that when you have y is 1, ln 1 is 0. Therefore, y can't be 1. These are some things you should be very, very conscious of when you are dealing with domains. You should know all the possible things that will eliminate the undefined. Therefore, you see that y should be greater than or equal to 0, but y shouldn't be equal to 1. We get it. Sorry, it shouldn't be equal to 0. We are dealing with, sorry, y should be greater than just 0. Good. Therefore, I'll have x comma y that length, sorry, so that y is greater than 0, right? And y is not equal to one. As simple as so. This is your domain. As simple. That's all about domain. Now let's move to the interesting parts of this course. We have what you call cylindrical coordinates, polar coordinates, and spherical coordinates. This is a true introduction to the beautiful mathematics you should. So starting with polar coordinates, okay? Polar coordinate, polar coordinate. What is a polar coordinate? The word is polar. Remember algebra. Whenever they say the polar form, you are interested in some two specific variables. One is theta, the other is r, where r is your what? Modulus, and we have theta to be equal to our argument. Now, the goal of polar coordinates is that there are certain function, multivariable function, which are two dimension. And these functions, if you want to integrate, you would appreciate it later. If you want to do integration of this multivariable function, we call them double integrals. You can never integrate them until you have converted them to the polar form. You would appreciate it later, as I keep on saying. So our goal here is for you to learn how to convert a Cartesian coordinate to a polar coordinate, of which I perfectly know that you know it. Just that the terms are just strange, but it's the same thing you know from algebra. If I have my xy plane here, right? Remember that if I locate any point in space and I trace it to the origin, what happens? The length here is my r, and the distance, angular measure from my x, positive x, to this line is what we call theta. Take note. Is what we call theta. Okay. So with this in mind, you have our x coordinates, which is the x here, right? And you have what? Our y here. So our x will be equal to what? R cos theta. Our y will be equal to r sine. As simple as that. So that is all about polar coordinates. So the goal here is that you should be able to convert from the Cartesian towards the polar, right? So let's see an example. Convert -4 convert -4 2 pi on 3 to Cartesian plane, Cartesian coordinate. How do we convert this to Cartesian coordinate? So here we are converting from polar to Cartesian. It's very simple. Using the equation s equals r cos theta, y is equal to r sine theta. Then the theta itself, remember, is equal to the tan inverse of what? Y on what? X. Like that. To know that. So here I simply have my r and my theta. My x will then be equal to -4 cos 2 pi on 3, and y is equal to -4 sine 2 pi on 3. What do I get? The answer should be equal to 2 comma -2 root 3. That's all. Then let's do another one the other way. So convert -1 into polar form, or into polar coordinates. Okay. Convert this into polar coordinates. What do we do? Remember the same thing. Our r is equal to square root of s squared plus y squared. Remember that from algebra, tan inverse of what? Y on x. Therefore, I'll have square root of 1 plus 1, because when I square become positive, which is square root of 2. Makes sense, right? So I have my r to be root 2. My theta is simply equal to tan inverse of -1 over negative. That is pi on 4. My polar coordinates are simply what? Root, comma, pi on 4. Simply that. Let's do the next one called cylindrical coordinate. Cylindrical coordinate. You appreciate that one. So cylindrical coordinate is nothing except the elder, let's say elder brother, slightly elder brother. They are very close, but one is having extra parameter. So cylindrical, yeah, all right, no. So cylindrical coordinates. For cylindrical coordinates, we are introducing an extra term called z, so that this z is away from our, sorry, so that this z is parallel to our z-axis. That's the thing. So we are looking at coordinates that resemble a cylinder or that create a cylinder. So if I have in space this, I have my x, oh sorry, I have my y and I have my x, right? I have my z. Remember that in the xy plane, you can have our, no, let me not do that. I will locate a point in space here. The point here is x, y, z. Okay, x, y, and z. Cylindrical coordinate has got three parameters. You know, polar was what? R, comma, what? Theta. Cylindrical coordinate is simply r, theta, then z. So take note, we've just added one more, which is z. Therefore, my point here in space, I can simply reproduce it on my xy plane like this. When I locate it here, I'm just projecting, okay? I'm just projecting. Realize that the angle from x to our point here is what? Our theta. The distance from here to here is our what? Our r, is sorted. Then this is our z point. Therefore, we have our r, theta, then c. What's the essence of this? The essence of cylindrical coordinates is very simple. It is just introducing a z. So you can see clearly that if this z, right, if I rotate it about my origin, what happens? I get a perfect cylinder. That's all. So one trick about, or sorry, one characteristic of cylindrical coordinate is that it is parallel to z, that I can create a cylinder. If I give you any set of coordinate for you to convert it to cylindrical coordinate, it's the same as you converting it to polar coordinate. It's not different. Just add the z part. That's all. Like I've given you point 1, 1, 2 to convert it from Cartesian to cylindrical coordinate. You use the x and the y and the z, so z will maintain, so you have 2 still here. This and this will become what? Square root of 1 squared plus 1 squared, that's square root of 2, right? Then this becomes pi on 4, as simple. So this is your cylindrical coordinate. So cylindrical coordinate is not difficult, but you appreciate it more when you do spherical coordinate. So let's talk about spherical coordinate here. Spherical coordinate. So this is a little bit somehow, I won't say it's messy, but it's not usual, right? I have my same x, y, z, right? So my x, y, and z. But there's something different that happens here. I'll locate a point in that point is not necessarily parallel to my z, but it is creating an angle with the that angle. We call it a special angle called phi. The distance from my origin to the point in space, which let's say I'll say originally a Cartesian plane with coordinates x, y, z. But the coordinate spherical coordinate is having rho, comma, theta, comma, phi. These are the spherical coordinates. Have all the coordinates in mind. Polar was r theta, cylindrical is r theta, then the z. Now you have changed everything and we are in rho, theta, phi. Where I've shown you where the phi is. The phi is the angle our spatial point is making with the z axis. Phi. Remember, we were able to project our points in space in the xy plane like we did for the cylindrical. So you surely have the component of what? The polar here. There will be theta here, which is always the angle x is making with what? Our points in the xy plane. Then the distance from our origin in the xy plane is giving us what? Our r. So you can see that it's the same thing. Then this is our z. So the difference here is the distance from our origin to the point, which is the spatial radius, is called rho. Let me add that, rho. Okay, rho. So therefore, the three parameters that defines a spherical coordinate is rho, which is the spatial radius. We have phi, which is the spatial angle making with what? Z. So the angle our point makes with Z is what? Phi, not theta. Theta is with the XY axis. Now let me show you something. Remember, you can clearly see that if I rotate this as it is about the Z axis, what do I get? I get a cone. This is because the angle I have chosen here is small. If I extend the blue line and I extend it this way, like this, and I draw, like assuming I've drawn this and I have pushed this one down and I have the point here. If I rotate this one to about the Z axis, what am I getting? I'm going to get a semicircle. So the spatial angle and the spatial radius gives what you call sphere, spherical. So you can get different. So this one is half of a meat pie. If you end up getting a complete um so assuming I have my negative z here, right? And I end up that my point is not making phi with z, but rather it is what? Making an angle of what? 180. I'm going to have that point moving round my plane, and that'll give me a perfect sphere. Because of that, the angle phi is always said to be greater than or equal to 0, but less than or equal to what? Pi. So this angle phi can never be greater than 180 because it gives us the angle of what? Rotation. So at this point, when I rotate, I get a cone. When I move forward, I'll get a semicircle. I move forward, I'll get some shapes B. So it's just a spatial angle. If you exceed it, it still repeats itself. So it's always lying between 0 and what? 180. Okay. Rho, as I said, is what? Is what we call the spatial arm, your spatial arm, the length. Okay, your spatial arm. Now let me create the 2D form of this so that we derive the equations nicely. In the 2D space of this, I'll draw my z. Now my z will become this, and on my x-axis will become my xy plane. So I've compressed the down one as a single plane and my z as a plane. Okay, therefore you bear me out that my spatial arm is here, and this is what? Rho. Is that not it? The angle here is what? Is phi. Is that not it? I'll have here. Always the angle the SY plane is making with this is what? Our theta. Don't forget. Don't forget. Therefore, this is what? Using the alternate angles. Our phi will come up here. Is that not it? Remember that this line here is our z. It is parallel to the z. Then the distance from here to here is our r. As simple as that. This is a compressed form. Now let's derive the angles and the formula for finding the different parameters of our spherical coordinates. Our rho, you can see the rho is like the hypotenuse. You can clearly see this is the rho. Okay, the rho is here, and now this is our angle. This is the angle you are looking at. So see it here. So let me turn it again. When I turn, I'll have my r here. I'll have my phi here. Then remember, this is our rho, right? Is that not it? Now I have my z down here. Okay. So using this, you can clearly see that my rho is always equal to what? Um, square root of what? R squared plus what? Z squared. Is that not it? Therefore, my rho will be equal to, remember R is what? S squared plus Y squared from polar coordinates. Therefore, if I give you any Cartesian plane, to find the spatial radius is simply S squared plus Y squared plus what? Z squared. As simple as that. This is our first formula you have to keep in mind. So that when I give you anything and tell you to convert it to spherical coordinates, you know what to do. Then after finding your rho, you need to find remember your theta is theta, okay? The theta within the spherical coordinate is the same theta you know from polar from cylindrical. So theta is equal to theta. That one I won't talk much. Or simply can say tan inverse of what? Your y or not x. Okay. Now let's see something. Here, you realize that our r here, what is r? R is simply equal to rho sine phi. And our z is equal to rho cos phi. These two equations can help us find r, can help us find z, and can help us find what? Phi. They are very powerful equations. Have all of them in mind, and let's solve a beautiful problem here so that you appreciate. So as usual, I'm going to have my problem here. Convert square root of 6 pi on 4, then root 2 into spherical coordinates. So this one I've given you is a cylindrical coordinate, root 6, comma pi on 4, comma root 2. Okay. Remember cylindrical coordinates, I have my r, my theta, and what? My z, right? And my z is root 2. And I'm to convert this into spherical coordinates. The first thing to do is you ask yourself, what do I need, or what are the parameters in spherical coordinates? So spherical coordinate is always what? Rho, comma theta, comma what? Phi. How do I determine my rho? How do I determine my theta? How do I determine my phi? Remember, theta is the same here. So you just carry theta. Now we know theta is pi on 4. You don't need to solve it. We are done. This phi here, we can only find it using the formulas. Rho, we can find it using the formulas. So we come here. Remember that rho is what? R is equal to rho sine phi. Then we also have z is equal to rho cos phi. But we definitely know that our, you can see here, rho is equal to what? Square root of r squared plus z squared. Square root of r squared plus z squared. Now we have r, we have z squared. So therefore my rho is simply equal to the square root of my root 6 squared plus my root 2 squared. That gives me square root of 6 plus 8, which is square root of 8, 2 root 2, right? Now I know my rho to be what? 2 root 2. Now I need my phi, then I'm done. To find the phi, what do? We simply come to this because we have our r, we have rho. We can find phi. So what's my r? Root 6 is equal to my rho 2 root 2 sine phi. Divide through by 2 by 2. I cancel. So phi is equal to sine inverse of the expression root 6 over 2 root 2. That gives you the answer. And that is all about conversion. So I just opened your eyes, introduced you to the whole concept of multivariables. We've touched on a couple of stuff. I mean, it's a little bit a lot, but you have to solve more problems and understand it from now. Otherwise, when you reach what you call triple integrals, double integrals, your head will burst. Thank you for being with us, and don't forget to subscribe and also follow through the journey, and you wouldn't get lost. So until then, just bye.